We recently introduced a procedure for applying the energy principle in multi-particle systems to find quantities associated with internal energy changes. The procedure applies the energy principle to the same setting, but in two distinct ways. First, the energy principle is applied to a simplified point-particle model of the original problem to understand something about the translational kinetic energy changes. Then, the energy principle is applied to the full multi-particle situation to solve for quantities associated with the internal energies, with help from results we obtained in solving the earlier point-particle model. In this lecture, we'll do an example. Let's consider the situation of a person jumping straight up into the air. Initially, the person, whose mass is capital M, is crouched down, motionless. Then the person springs straight up. At the instant the person's feet are about to leave the floor, we observe that the displacement of the person's center of mass is upward with a magnitude of d, and that person's center of mass is moving with speed v sub f. What is the change in the person's internal energy? Let's choose as our system the jumping person, and let's first apply the energy principle to the simplified point-particle model of this system, where we are focused only on the center of mass motion. Here's the sketch for this. Our energy principle here focuses on the change in translational kinetic energy and connects that to the work done on that system as it displaces through the center of mass displacement. We have enough information to determine the change in translational kinetic energy. We have the initial and final speeds as well as the mass. However, we can use the energy principle on this simplified model to solve for the unknown surface contact force, the force of the floor on the person during the jump, if we assume that force is constant during the jump. For the point-particle model, the weight force does negative work, and the surface contact force does positive work as both act through the center of mass displacement. Putting all this into the energy principle, we can solve for the force of the floor on the jumper. Now we can return to the full multi-particle system and apply the energy principle. In the real system, there are more changes in energy than just translational. The jumper's metabolism involves chemical energy changes and thermal energy changes. The movement of the jumper's limbs involve kinetic energy changes that are separate from the translational kinetic energy change. We'll lump all these internal energy changes into one composite change in internal energy, which we're trying to find. Now, by the energy principle, this is equal to the work done on our system, which is the jumper. We still have the same forces: the floor force, the weight force acting on our system, and the work done by the weight force is the same as in the simplified system, since the weight force is, in effect, acting at the center of mass, so the center of mass displacement is used here to find this work. However, the floor force in the real system acts at the jumper's feet, at the floor, and during the act of jumping, the feet are always in contact with the floor and do not undergo any displacement. So, with no displacement, the floor force does no work. So in the full multi-particle problem, the total work done on our system is just that work done by the weight force. We rearrange the energy principle to solve for our unknown change in internal energy, and we plug in what we know to obtain the final result, our solution to the original problem. Let's just interpret this. We see that the change in internal energy is negative. This means that there is an overall loss of internal energy, which shows up in part as an increase in translational kinetic energy of the jumper and in part as energy transferred out of our system, the jumper, by the weight force. That's it for this example. We'll do another example in our next lecture.